The CISSP class, and we're down to chapter 3, and I'll start with that. Perfect for the presentation. I want to write about the overuse of AI. Absolutely. Oh, by the way, you should be, your topics are due today, so you should put in, it doesn't have to be much, just a few words like a title, just so we know you're thinking about it. And then you can start presenting next week or the week after. Well, I figure most people will wait 2 weeks, but people that do it next week get extra credit. And people that are later lose some points, but anyway, you should be thinking about your presentation and getting ready. And you should at least know what the topic is tonight. Anyway, so let's take a look at the slides of chapter 3, which is here. There. And we did the first little bit of this last time. Good, that's right where we are. All right. So we talked about the Bell LaPadula model and the BIBA and the Clark-Wilson model, the first 3 major models as we invented what the concept of cybersecurity is. And from that, we learned that we have to consider confidentiality, integrity, and availability, which was not obvious. I know, like most people, I just thought security was confidentiality. These other things didn't occur to me or anybody else until we tried doing it and found out that there's more to it than confidentiality. So here's another model, information flow, where you limit how information flows in the system. Technically, both Bell, LaPadula, and BIBA are this type of model. A Chinese wall model is something that comes from law firms. If you're representing somebody in a lawsuit, and then somebody on the other side wants to be represented by the same company, one answer would be, we can't take you on. But the alternative is to let certain people in a company take each side and have what they call a Chinese wall, have a limitation of what information they share, so that they operate as if they were separate companies for the purpose of that case. And that's a way to avoid this. All right. And non-interference is a property you want of your computer systems, where it means that if data is processed at a high security level, it has no effect on what happens at a lower security level. That way, there should be no way for people without sufficient privileges to find out the secret information. This is a desirable property. If this fails, you have a covert channel where somehow secret information is leaking out. And so, for example, you can measure the power consumption of the box, which is not top secret, and from that you can deduce a top secret thing like a cryptographic key. This happens a lot. All right. In fact, this is what you want. In fact, it is very difficult to provide. There's the take-grant model, where you have rules like take, grant, create, and remove, and you have a complex set of relationships. Someone can take a privilege, you can grant a privilege to someone else, create a privilege, and remove it. So Alice can create and remove privileges to secrets. She can grant privileges to Carol, and Bob can take Alice's privileges because he's her superior. So this is another way to structure it. All these models do approximately the same thing, just in different ways. Then there's an access control matrix. This is what you'll see in a Windows system. You can have read, write, or execute permissions. It looks like Linux here, but it's similar, for different people to access a file or a folder. And so the Graham-Denning model has rules like this: transfer access, grant access, create object, destroy object, and so on. You see, they're all doing very much the same thing, just like all those compliance frameworks, some way to limit what people can do. There's the HRU model, which is the same but only has 6 operations, treating subjects and objects the same. All right, and then there's modes of operation. This is a tough one. There was a time when in the Pentagon, some people had as many as 7 computers on their desk, because your top secret machine had to be completely separated and air-gapped from your secret, from your confidential, from your public machine, and so on. And in order to get away from that, they tried to move to a different system, from multi-level system, to make it much cheaper and easier to set up. But here's the 4 modes of operation: dedicated, system high, compartmented, and multi-level, and these are U.S. military specifications. So dedicated means the one I just described. If you have secret information that is completely separate from other machines on a totally separate hardware, then the top secret and the unclassified. Everyone's cleared for this level or higher. Everybody has access approval and need to know. So this is what you do if you don't trust the technology to sort the data. You just put it on the system, and that's it. Everybody with access to that system is cleared to see it. Nobody else is allowed to see it at all. A system high is where the object has mixed labels. You might have confidential, secret, and top secret data on the same machine, but all subjects must be cleared up to the highest object. So that's another way to do it. Compartmented means Everybody has the necessary clearance, but they don't have formal access approval or need to know, so the objects are placed into compartments, and technical controls enforce need to know. So you might be the expert on China, so when you access the system, you're only allowed to see the information relevant to China, but somebody else who's the expert on Russia would see the information about Russia, and so on. But all the information is really on the same machine. It is, you trust the machine to remember what your horizontal privileges are and limit them. And the last one, of course, is where you trust the machine much more. You have objects of different sensitivity labels and different clearances, and a part of the operating system is a reference monitor which controls access. So if a top secret person logs in, they can access the top secret object, but if a secret person only cleared up to secret tries to, it'll be denied. And this is where you actually trust the operating system to sort the people and enforce all the privileges, horizontal and vertical, and now you could have just one computer shared by people at many different levels. And therefore it's much more efficient and much cheaper, but technically a little riskier. So, how you evaluate these things, TC-SEC was the standard one, called the Orange Book, defined in the 1980s. The international models came later, IT-SEC and Common Criteria. A book looked like this. This is the 1983 Orange Book, part of the National Institute of Standards, and it rates security levels from A to D. So D is minimal protection, none at all, basically like MS-DOS. C is discretionary protection, where you have an owner of the object, and the owner decides who can do what with it. B is where you have mandatory protection, which means there must be a higher authority telling you what clearance you have. And then verified protection is the highest. So the Red Book is the network version, having similar concepts on the network systems. And IT-SEC is the European one, which came later and is intended to replace the other one, although I think the U.S. still uses this, so I guess I'm not really sure what they do in the military. But it separates functionality and assurance. Functionality is how the system works, and assurance is ability to evaluate the security of a system. And we talked about this many times. You set a security goal, then you implement some controls to achieve your goal, and then you measure the effectiveness of your process. You don't, because nothing is ever perfect, you say, how many people were in fact able to access the wrong thing according to this system? Things like effectiveness and correctness are the measures of the success of it. So you have E0 is inadequate, E6 is the formal model, and you can compare the two. So E0 is like D, and A is like F up here, and so it goes on. You can compare them together. It's kind of a mess, but anyway. That's functionality. Functionality of E, functionality of C, and B takes you through these various levels. All right. Anyway, then there's International Common Criteria, which is supposed to supersede both of them and be the most modern system. So you have a target of evaluation, the system you're evaluating, and you have a security target, which describes what you're trying to accomplish, what the security levels you'd like to have are. And then you have a protection profile and an evaluation assurance level, which is the score of the tested product. So they all do essentially the same thing. You define your security policy, you implement it somehow in technology, then you test it somehow to see how effective it is and give it some kind of rating. Right, and maybe I better close that door again. They always seem to get noisy up here sooner or later. There's only two classes on the floor. It reminds me of when cars were new. I think there were only two cars in the state of Kansas, and they rammed into each other. So, anyway, all right. And so here's functionally tested, structurally tested. So this means it works at all. This means the structure of it is according to some rules, then methodically tested and checked, then reviewed, formally designed and tested, and formally verified, designed and tested. So one thing that happens is you have a whole lot more managers and a whole lot of paper and document and proof flying around at these higher levels. And this, I think, is why there's the famous thing, I've heard of complaints all my life, like the Pentagon, if they buy a hammer, it costs $800, because all their equipment has to have all this blizzard of paper and management, making sure it's good. Anyway, let's try a Kahoot. 3B is here. till the end of the song. Better wait another bit longer. People still coming in? Okay. All right. I guess we got everybody now. All right, so what security feature prevents a covert channel? That's non-interference, that the processing of the high privilege data does not have any effect on low privilege data, so the low privilege people cannot deduce what's going on at the high privilege level. All right, so what operation mode enforces an air gap between each security level? That's dedicated. The hardware is dedicated to one security level, and you have to have different hardware for the next security level. All right, which mode uses a reference monitor to control the access? That's the multi-level system. You actually trust the operating system to make people log in, not get mixed up, label all the objects, keep all the labels correctly, and actually handle multiple levels of people and multiple levels of data and not let people break the rules. All right, so what TC-SEC level does your home laptop fall under? C. D is like an old floppy disk. Presence of the disk means anybody can read and write on it, no control at all. C, in a modern Windows laptop, you do have to log in, and the owner who can log in can then decide who's allowed to read and write on there, so it's at your discretion. This is discretionary protection. You own the machine, you own all the data on it, and you can decide to share it or restrict access. All right, what's the modern international standard security evaluation method? common criteria is the modern system. Replacing both of this is the Orange Book, this is the earlier international system, this is the new system supposed to replace them both. All right. Good. So, all right, so let's talk about secure system design. One issue is layering. This is a big issue. You have the 7-layer OSI model for networking, and you have other layers here. The point is, early computers were just one device, but as they got more popular and you started selling different pieces of hardware, you might buy a different hard drive or a different modem or a different processor for different machines, so it became necessary to give them each layers. So the hardware is one layer, kernel and device drivers are the heart of the operating system that must always be in memory and that run with full privileges, able to execute every command on the processor. Then the operating system above that enables you to run applications here at a lower level of privilege, and when the application crashes, it doesn't cause the whole machine to stop, whereas if the kernel or device driver crashes, it does. So you have these layers of performance, and the point is changes at one layer don't affect the other layers. That's the idea. So that's one issue, is layering. Another one is abstraction, where you hide unnecessary details from the user. So you open up a browser, you play a movie, you just see the movie, you don't see the individual bits, you don't see the MAC addresses, the IP addresses, you don't see the error correction and the retransmits on the wireless network. There's all kinds of stuff going on behind the scenes that the engineers and software authors know, but the end user doesn't need to know any of that. They just see something like a desktop with icons. They see a virtual environment that they can live in, which is kind of a lie, kind of an illusion. All right, so then you have domains. Like I mentioned, kernel mode is the highest level privilege in the computer, and user mode is the lower privilege, where things like Microsoft Office and other applications run. So that if an error occurs here, it doesn't affect kernel mode, the computer continues to run, just this one program stops, and the rest of the operating system can pop up a message and say, your application has crashed, would you like to relaunch it, and things like that. So there are actually 4 rings of privilege on the motherboard and in the processor, but no modern operating system uses them all. The only thing we actually use is ring 0 and ring 3. These others were, there were operating systems that used them, but they've gone extinct. It just didn't turn out to be popular. All right. And so hypervisor mode is the new one called ring -1, and this is because virtualization became so popular that people wanted to run virtual machines a lot, and they didn't want them to run slowly. So they created hardware-assisted virtualization, which means your virtual machine can use the operating system, the CPU instructions without any translation, and theoretically can run as fast as the host machine. So that's the idea. They call it ring -1 is one way to look at it, but those are the hardware-assisted virtualization, and as you probably noticed, if you install VMware these days, you are forced to go in the BIOS and turn on hardware-assisted virtualization. It won't even install anymore without this on machines. So an open system is one where the specifications are published, you know what chips are in there, you know how the operating system works, and so on. This is what IBM did. IBM made a public PC, and it turned out to probably be a bad idea. IBM never made any money from the PC because they were so slow at manufacturing it that amateurs made more powerful machines that were compatible with it and sold them cheaper. Now, closed system is like Macs, especially before they switched to Intel. Macs would not even put the numbers on the chips. Everything was secret. Everything was closed. You could not build your own Mac hardly at all. They made it as difficult as possible. That's a proprietary system. All right. Then you can have a secure hardware architecture. You've got system unit is the computer's case that has all the internal components like the processor and the RAM and the hard drive these days, and SSD usually. The motherboard has slots to attach these devices. And there's a computer bus. The CPU itself has an arithmetic logic unit and a control unit inside it and some registers. It then connects to the RAM, and this is where most of your processing happens. The CPU processes data and it reads and writes to RAM. Then when you want to save something, you save it to the hard disk or the SSD or the CD, and then you have the display and the keyboard mouse here also connected. And buses are what connects these components together. Yeah?
A always opposite of advanced logic unit?
Arithmetic logic unit. Yeah, this does arithmetic and logic. Yep, very good. Right, and so, all right, so then there's North Bridge and South Bridge in modern computers. The North Bridge is very fast, and that's so the CPU can talk to the RAM and it can talk to the video memory, so you can have rapidly changing images like video games. And the South Bridge is slower, and that's where you put slow things like the hard disk and the keyboard that don't need to have it in just microseconds. All right, so the CPU, the arithmetic logic unit, performs mathematical operations, and the control unit fetches the instructions from RAM and hands them over to the ALU one by one. So there's a cycle that goes on: fetch instruction, decode instruction, execute it, and save the result somewhere. That's what happens in every clock cycle, and most instruction takes several clock cycles, like maybe 4 or 6 clock cycles in an Intel processor. Interrupts are how all modern operating systems work. They wait for a request to service. Most of the time, they're just sitting there doing nothing, idle. They wait for a signal telling it time to do something. That's what happens, telling you have to stop your current task and serve the interrupt. So a task is broken into threads because it is one huge problem in computing is that all the devices run at very different speeds. Like the keyboard is extremely slow. That waits for a human to respond. That will take seconds. The hard disk takes a lot of time. The RAM is much slower than the processor. So you very often have a device that can run really fast waiting for some slow thing to happen. And so to avoid wasting all that time, you break each process into threads. So one thread of instructions is waiting for something from the hard disk, but while that's waiting, other threads can move forward, doing some other part of the job. That's multi-threading. All right. And multitasking and multiprocessing, all modern computers are multitasking. They can run several programs at once, even if they have only one CPU, because they don't really all run at the same time. They each get a certain strobe, a certain portion of time, and then the other one gets more time, and the next one gets more time. It looks like they're all running at the same time to the user, but they're really taking turns. Multiprocessing is also usually the case now. Usually you have more than one CPU core on modern machines, which means they really can be doing multiple things at the same time. Symmetric multiprocessing uses one operating system for all of them. Asymmetric one have a different image per CPU. And by the way, GPUs have hundreds or thousands of cores, and they all run independently, but they all have to execute exactly the same instructions. So they're intended to be doing something like rotating a 3D image for a video game, but they can be used for AI, tensor mathematics, or for cracking passwords. But you have to write the code understanding this, and I'm teaching a class in that in another college. It's very interesting to learn. Yeah.
Video games, they need only high-resolution graphic card.
Yeah, that's right. Modern gaming graphics runs on the GPU, yeah. And modern AI runs on a TPU, a tensor processing unit, and both of those have many, many cores that all move together. So you've got a timer that reboots the system after something crashes, and you've got direct and indirect addressing. So here, if I add EAX 8, then I will take the immediate value 8 and add it to EAX. So EAX is the storage register on the processor. It contained a 1. After I execute this command, it will now contain a 9. If you put brackets around the 8, this is basic assembly language programming, then the 8 is interpreted as an address. So I go to address number 8, find the data there, and put it in EAX. So if that contains 5, EAX will go up to 6. And then there's indirect address. Add 8 to the address specified by EAX. So if EAX contains 12, you go to location 12, find the address, and then add 8 to that. So this is direct and indirect addressing. All right. And there's memory protection. Each process is assigned a certain amount of memory to use, and it's separate than the memory in other processes, and you don't want them conflicting, of course. So they're all sharing the same hardware, but the operating system gives each process a little piece of memory to use, and it can only use that memory. That isolates them. There's a logical control to prevent one process from interfering with another. So they work by virtual memory. All Windows programs think they are at 400,000, but they're actually relocated somewhere else in memory. And there's object encapsulation we'll get to, and I mentioned time multiplexing. Each process, each thread gets a certain number of clock cycles, and then the next thread gets some clock cycles, and then the next thread gets some clock cycles. That way they all move forward by taking turns using the processor. And when you switch from one to the next, that's called a context switch. You have to save all the information to remember where you are and move to the next one. Now, when a processor starts, it recapitulates the history of computing. When it first starts, it runs in real mode. This is the way really primitive computers were, like the MS-DOS computers, that could only run one program at a time. They had no ability to run two programs. I remember using these things. You would have to print out your document, and then you would have to open a graphics program to make the images, and then you'd have to cut up tape and tape the images on the paper, because there is no way to run a word processor and an image processor at the same time. But anyway, now that's what's happened in real mode. No process isolation. Any process can write anywhere in RAM. That's where it starts. Then it switches to protected mode and moves forward. So it goes through stages during boot up. And there's a lot more to it. And if you listen to Paul's Security Podcast, Paul Asadorian is an expert on this stuff. Non-modern secure boot goes through many stages of cryptographic verification as it boots up to try to stop anybody from compromising the operating system at that level. And there are viruses that do take over the boot process, and or attacks that do that. And there's a lot of attempts to stop that. Anyway, it's quite a mess, the first few stages of boot up. So virtual memory maps the hardware memory to processes, and it allows you to isolate them and also to swap pages in and out of RAM. Because if you keep opening windows, you open a browser, you open a game, you open a movie player, pretty soon you've got so many things running they can't all fit in your RAM, so it takes stuff that you don't seem to be using and puts them on the hard disk or SSD for temporary storage. That's called swapping. And if you try to access memory, but the memory is no longer in RAM, it's on the hard drive, that's a page fault, and now it swaps them back, and the result is, normally it works fine, but it slows you down, because you have to go to that slow storage medium, so you can run a whole lot of things at the same time, but at some point, things start slowing down. So BIOS is the code in firmware. When PC is first powered on, it runs a power on self-test to see what's attached, because for all it knows, the reason you turned it off was to change something, like add more RAM, change the monitor, change the keyboard. So first it tries to detect to see, what do I have? If it finds a boot device, it boots from that. It also requires certain devices. It usually demands I have to have a keyboard, I have to have a storage device with an operating system, and I have to have a monitor. If I don't have them, I'm not going to start. I'm going to just pop up an error message and say, I don't appear to be a computer. You've taken away too much stuff. Write once, read many. This is the kind of stuff you have in CDs and DVDs where you cannot alter it once you've written it once, like commercial movies and such come this way. The Trusted Platform Module is a term from the Orange Book. That's because they wanted Microsoft operating system to be usable by the military, so they tried to design it to meet the military specifications. And the Trusted Platform Module is there to create a trusted platform where you can trust it for security. So it's a cryptographic coprocessor, and it can securely store keys. The keys for cryptography are stored inside the TPM, and they are not anywhere in the address space of the processor. So no code running on the processor could possibly steal the key. All the processor can do is ask the TPM, please encrypt this stuff, and ask the TPM, please decrypt this stuff, but it never sees the key. That's the idea. All right. And so data execution prevention is a modern security feature where you can now put permissions on areas of RAM. It's been around since Windows Vista for quite a while now. And so you can mark areas non-executable, and that means even if someone manages to inject code there, when they try to run it, it won't run. It will just be an error. You're not allowed to run data there. You're allowed to store data, read it and write it, but you're not allowed to execute it. And this stopped a whole generation of viruses that affected Windows XP and earlier Microsoft systems. Address space layout randomization also helped. Now, every time you launch a process, it randomly relocates it in RAM. It doesn't just take the lowest available RAM, which is what MS-DOS used to do. And so, or what Windows 95 used to do, I should say. And the point is now, you can't tell where you are. Every program thinks it's at 400,000, but it's really somewhere else. So even if you gain the ability to inject code, you can't find it to run it. There are ways around this. There are ways around every defense, but these were the giant steps forward for security in Vista, which was much more secure than Windows XP, and every version of Windows after that has continued to get more and more secure. Microsoft has been taking security very seriously, and in many ways they are a security leader these days. All right. We all used to mock Microsoft for being pathetically insecure, but that is no longer true. They've really improved. All right. All right, so what ring does user mode use? Ring 3. Ring 3 is user mode with the lowest privileges. It cannot directly touch the hardware. All your user mode programs can't directly connect to the hardware. They have to call an API call to call a kernel routine to please touch the hardware for them. All right, users can't handle the truth, so the computer lies to them. What is the term to describe this situation? That's abstraction. You present them with an illusion like a desktop and a folder and files in the folder, and the reality is far more complicated than that, but they live in that illusory world. And they can it's true enough for them to get things done, but the technician has to understand the details behind that to fix the system. All right, what communication channel connects the components? That's the bus, all right? All right, if I launch Microsoft Word, what have I created? Created a process, and the process contains many threads. But that's the name of the process, Microsoft Word. All right. And which one is the cryptographic coprocessor? That's the Trusted Platform module. And this is a big irritation for people using Windows machines because for Windows 11, you must have the TPM 2.0. So most of the hardware for Windows 10 will not run Windows 11 because it only has the 1.1. Many people are annoyed by that. Anyway, all right. 20, all right. Whoa. Good. All right. I think we'll do one more before we take a break. All right. So the secure operating system and software architecture, we already talked about this. The kernel runs in ring 0, always in memory, with full privileges to use the hardware. And there's two types of kernels. Monolithic kernels are compiled into one static executable, and you have to recompile the kernel to add new features. This is faster, but less secure against crashes. And Unix and Linux use this system. In the most extreme case, there's Slackware, where you have to recompile the kernel for every new piece of software you add. Microkernels are modular and have less native functionality, but they can add functionality via loadable kernel modules, so you can add new software without recompiling the kernel. Instead, you just add a module to the kernel, and this is slower, but more secure against crashes. Windows is closer to a monolithic kernel, a hybrid system. And I mentioned before, the reference monitor is a term from the Orange Book. This is the security part of the system that keeps track of who everybody is and what their privileges are to access enforces the system security policy. It's always enabled and cannot be bypassed. And a secure system can evaluate the security of the reference monitor, and you cannot reach A and B levels without having a reference monitor and the TCSec. So in Linux and Unix, they use read, write, and execute permissions. You'll see there's a folder, something called header. It's a file, and it's read, write, and execute for the owner, only read and write, only read for the people in the same group, and only read for others. There's these 9 bits are the security model of Linux. 3 bits for read, write, and execute for the owner, 3 for people in the same group, and 3 for everybody else. That's the fundamental way privileges are handled in Unix and Linux. In Microsoft, you have these things: read, write, read and execute, modify, and full control, and you can determine those levels for groups of people like everyone, system, people assigned to administrators, and so on. Actually, there are 14 bits, individual permissions, and these refer to certain combinations of those bits. It's pretty complicated, but if you take a Windows operating system class, you learn all that stuff if you get your Microsoft certifications. All right, and there are privileged programs in Linux that run like password, where a non-administrative user can run this program and it will elevate to administrator enough to write to the password file and then come down. So this is a special program that runs as the owner even if it's launched by someone else. And they are a security risk, and the most modern versions of Linux have gotten rid of them somehow. All right. Then there's virtualization, of course. In distributed computing, virtualization is where you run a program called a hypervisor that simulates hardware. It simulates a hard drive, the RAM, it assigns some RAM, the RAM is not virtual, and it pretends to have a processor that might be different than the real processor and so on, and then you install an operating system in that simulated environment. So full virtualization is where the simulated hardware is completely independent of the real hardware, and this is what you get with QEMU. You can change the processor, and if I'm running an ARM processor on this Mac M1, but I can run its emulated Intel processor. The problem is there's a huge performance penalty for doing that, but you can do it. Paravirtualization is more common, where the virtual hardware is similar to the real hardware. For example, it must have the same processor. You're not really altering the processor. Then it can be more efficient. It runs a lot faster. All right, so the hypervisor controls the access between the guest operating system and the host hardware. So Type 1 hypervisor runs directly on the host hardware, and this is what VMware ESXi does, the most common thing used to run clouds. Type 2 hypervisor, like VMware Workstation, runs on top of an entire operating system like Windows, and that is much slower, and it's mainly used just for training purposes. It's not something people would use for serving up a server on the internet because you're wasting a lot of the performance running a whole operating system under it. All right, so the point of virtualization is you can use all your hardware to its maximum extent. Before virtualization, most cloud servers were running at like 20% of capacity because you'd set up a server, it's like a web server, but you don't have too many people using the web server, and there was nothing much you could do about that. Now you virtualize everything, and you can run all your hardware closer to its full capacity. You can also make backup and recovery easier, and you can make virtual clusters of guests, and this is what you do with modern VMware with vSphere. You have a storage area network storing all the contents, you have multiple computers hosting the machines, and you spin up more machines to handle heavier load, and then you take them down, and you can migrate the running machines from some hardware to different hardware without shutting them off to replace this hardware, and so on. And this is what's going on in the Amazon cloud and advanced cloud services. So you get there are security issues now. This means you have many different guests running on one host, and in principle, one could leak into another. There are occasionally VM escape attacks. So like the multi-level computer we talked about in the previous section, where you have multiple levels of security on the same machine, and you're trusting the operating system not to get confused, now you're trusting your virtualization software to not get confused and let the data from one virtual machine leak into another virtual machine. So that's an issue. And the other problem is suppose you have 4 machines running on one host. Then you have one network connection they're all sharing. Well, you can monitor that network connection and you'll get all the traffic to the internet, but the traffic going from one virtual machine to the other on the same host never goes out the network card. It passes through a virtual network card from one machine to the next, so you might not be able to see that traffic to monitor it. It's another issue. Anyway, and so here's cloud levels. You've got infrastructure as a service, and platform as a service, and software as a service. So with infrastructure as a service, somebody rents you some hardware, and you can put whatever operating system you want on it and whatever applications you want on it. Platform as a service, you get some limited capability to modify it, like my web hosting. I can put any web pages and scripts I want there, but I can't get to the operating system. And then there's software as a service, where you can just run one application and you don't even know what server it's on or what version it is or anything, like Gmail. You can use it, but you have very little control over it. So a private cloud is where you own the hardware and run it on your own hardware, and you make a cloud so it can be accessed by your workers that are spread all over and remotely. This is what government clouds often do, and it's what a lot of companies do. Then you know you control where the data is. The public cloud is, of course, things like Azure and Amazon and the Google Cloud and the Oracle Cloud. They're extremely popular. But the problem is you've handed all your data to somebody else and you don't really know what they've done with it. You don't really know if they've secured it properly. You don't really know where the backups are. You might not even know what nation it's in. And so that's an issue. And this happened in Amazon. And Amazon had some images. They used to let users put up images and you could copy them. So somebody put up an image and it had an SSH key that was the same on all of them. So anybody could get in. That's the problem if you have a machine copied from sort of an amateur. And also another thing that happened, I don't know if I got it here, in the first days of Amazon Cloud, they didn't wipe the disk between one user and the next. So somebody would just rent a machine and run a forensic tool and find the last guy's data on there. They fixed that. But that's the thing. How do you know that hasn't happened? There's a way to know, by the way. A guest came to give a talk here, an expert on Linux. He explained how to make an operating system, minimal Linux, that runs in RAM, make a connection to it, and from there, wipe your hard drive and verify that it's wiped before you decommission the machine. It can be done, but it's not simple, and most people don't think of that. Anyway, then there's grid computing, where you combine dissimilar machines. This is not very common, but it is used by SETI at home and Folding at home, which are, big, where you get people to volunteer some time. Anyway, large-scale parallel data systems give you high performance, sharing memory between systems, and therefore you might have race condition vulnerabilities. If two systems are accessing the same memory, one of them might write something and then come back to read it, and before they read it, somebody else has written something else in there, so you get confusion. And these are called the race condition vulnerabilities. Right, and then there's peer-to-peer systems like BitTorrent, where you share data between many systems. And I guess you could call Bitcoin this way too. You can't take it down easily because it doesn't have a central server anywhere. You take down some of the machines, the remaining machines continue to do it, and so it's used to copy proprietary software. All right. By the way, BitTorrent does break every file up into chunks, and it has a hash to verify the integrity of every file, so it's pretty good at making sure the file you get is intact and unmodified. The problem is, since it's mostly stolen property, some of it contains malware by the person that put it up there, and all BitTorrent does is efficiently and correctly deliver the malware to you. It doesn't have any way to know that it's not malicious. All right, and then there's thin clients. You can have machines that do not have any storage at all. They're just a keyboard and a monitor, and they connect to a server, and all the processing happens on the server. So that's one way to do it. This is actually how all my consulting goes. Everybody gives me nobody wants to use my own hardware for anything. They give me a virtual machine on Azure, controlled by the company, and I just connect to it with a client. That way, all the company data is on there. There's no way to copy it to my home machine. It's a pretty good policy. That way, they don't care what I'm using. They don't care if I'm infected by a virus. It doesn't matter. All the data stays on the cloud machine. All right, and that's like I said, diskless workstations can do this, where they load the operating system and everything over the network. These were all the rage a while ago. Haven't seen them that much lately. And then, of course, the Internet of Things. Everybody has all these gadgets. They're all connected to the internet, and they're all smart, and they can all be attacked. And that's the problem. They tend to be as cheap as possible, so they tend to have terrible security decisions like default passwords, buffer overflows, command injection, all kinds of stuff. And there's a lot of botnets that take over these home devices, and so that's the current situation. Anyway, let's take a look at another Kahoot. Aha. All right. I'll wait another line or two here. Somebody's flipping in and out. Maybe they have a bad internet connection or something. All right. All right. So what do you need for TC-SEC Level A? Okay, you need a reference monitor, or you can never make it to A or B. All right. All right. Which is a security risk of virtual machines? Yeah, VM escape. Code on the virtual machine is able to affect the host or other virtual machines. That's not supposed to happen, but sometimes it does happen, and that's a security flaw. All right. What kind of service is Canvas? what you're using for quizzes. It is software as a service. You're just able to use that one program. You can't uninstall it. You don't control the operating system or the hardware. You're just using one program, whatever features the service provider chooses to let you use. All right. And what system combines dissimilar computers together to get more CPU power? That's grid computing. All right. All right. Stop this. All right, and I see some questions here. The topic that's due today was the first quiz on this part. The quiz is due, and if you're late, just do it anyway. And the presentation is a short 4-minute talk on any security topic. And what you should do today is choose your topic and send it in. If you can't do it today, do it as soon as you can. Just the title, just a few words to describe your topic. And in 2 weeks, you give a 4-minute presentation in class. Or you can record it as a YouTube video if you want, but it's got to be only 4 minutes long, and we will watch them, and it should make some kind of point about security. So let me stop the recording.